Howdy, my name is Patel, and I'm an undergraduate computer science student from Texas A&M University. For the OREU program, I'm working on a project called Automated Strain Analysis and Mapping using TEM diffraction data. My mentors for this project are Dr. Kelvin Shi and Daxin Zhao. I'm also working on this project with Aaron Barbosa. The image on the left shows the TEM diffraction data that we get. Each pixel in the image corresponds to a diffraction pattern, such as the one shown in the image on the right. The goal for this project is to create a program that accurately recognizes the center of diffraction spots in diffraction pattern and then uses the positions of these spots to create a strain map of the data. While there is already commercially available software to do this, it is inconsistent with the accuracy of its calculations and is slow. Some files need to be kept running overnight for the analysis to be complete. We plan to create a program that is more accurate and faster than the one available. The first issue we need to resolve was to find a way to identify diffraction spots. Fortunately, we came across a Python library called Pixtem that did just that. The top image shows a diffraction pattern using Pixtem to find diffraction spots, while the bottom image shows a diffraction pattern using the commercial software. We then created the program that went through each diffraction pattern in the dataset, identified the spots, and then created the strain map. To make the program easier to use, we added a graphics user interface shown in the image to the left. We also added the option to visualize the analyzed data as either a bar chart or a heat map. With the base program completed, we moved to optimization. One of the biggest issues we ran into was the program's runtime. We solved this problem by using multiprocessing. Python generally is locked to using only one CPU core due to the global interpreter lock. Since the program had to perform the same list of tasks for each of the several thousand diffraction patterns, the load could easily be distributed among the several CPU cores. The use of multiprocessing significantly reduced the runtime of the program. For example, a certain file that took 45 minutes to complete before now was completed in 80 seconds. While multiprocessing significantly reduced runtime, it came with a few issues of its own. The first issue is that the runtime is now heavily dependent on the CPU being used. A CPU with more cores and a higher base clock performs much better than a CPU with less cores or a lower base clock. The second issue is that the whole file must be loaded into system memory before analysis can begin. This could be an issue with bigger files exceeding one's system memory. While both these issues can easily be fixed by buying a better CPU or more memory, it is something to keep in mind. Next, we shifted our focus to the accuracy of the identified spots. We experimented with 3 different image filters: the non-local means filter, the Gaussian filter, and the Wiener filter to see if they helped increase the accuracy of detected spots or helped identify more spots. The first row of images are all taken from the area identified in the diffraction pattern to the top right. The leftmost column shows the area originally, and the rest of the columns show the same area after each filter is applied. The second row of images are a 3D representation of the images in the first row. Finally, the last row shows the diffraction spot recognized after each of the filters is applied to the same diffraction pattern. As clearly seen, the use of filters improves the number of spots identified. As mentioned before, we have been using a Python library called Pixtem. Although Pixtem performs better than the commercial software a lot of the time, we felt we could do better. We created our own diffraction spot finding algorithm that used template matching with the center beam diffraction spot as a template. This resulted in more diffraction spots being recognized, greater accuracy in detected spots, and clearer heat maps. The picture to the top shows a heat map of a file using our own diffraction spot finding algorithm. The bottom picture shows a heat map of the same file using PixSim. Comparing the color bar values, we see our method is more accurate. Through visual inspection, you can also tell our method produces a heat map with less noise. Finally, to test the correctness of our program, we use the sapphire sample as shown in the top picture. The bottom picture shows the strain map our program created. As most of the data is between negative 0.5% and positive 0.75%, we can consider our results realistic and fairly accurate. Dr. Shi and Dakshin were satisfied with the results, and we are currently writing a paper on the process. Future plans. We plan to rewrite the code to be more readable and add more comments so we can publish the code with the paper when it's ready. Our next project is to write a program to automatically label different orientations of diffraction patterns in a single file. Thank you for watching.